Welcome back, student. Now let's take a numerical on a compressible fluid flow. In the previous lecture video, we already discussed on the various topics of compressible fluid flow, like velocity of different types of medium and critical properties, stroke flow, and different types of one-dimensional steady isentropic flow. This topic we already covered in the previous lecture video. And now let's take an example, or let's take a numerical on this. And now the numerical is that a convergent divergent nozzle has a throat area 500 millimeter square and an exit area of 1000 millimeter square. Air enters the nozzle with a stagnation temperature of 360 Kelvin and stagnation pressure of 1 megapascal. Now we have to determine the maximum flow rate of air that the nozzle can pass and the static pressure, static temperature and static temperature and Mach number and the velocity at the exit from the nozzle. If the condition is given that if the divergent section act as a nozzle and divergent section act as a diffuser. So in this problem, what is given that? So basically a nozzle, which is basically a convergent divergent section. So this is given here, and the throat area. Now throat area is given as 500 millimeter square. So the throat area is given, and you know that the convergent divergent section. It looks like this one. And suppose this is a duct in which you can see that the converged sections. This is the converged section. So this is suppose this is a duct section. This is throughout this is a duct. You can say that. Now in this duct, it is a converged section. In this section is called basically throat, and this is called divergent section. Okay. Now this is the convergent, throat, and divergent. And this is the inlet section. This is the outlet section of the duct. So this is the pictorial diagram actually of this numerical, in which the data is given as the nozzle. So basically convergent divergent nozzle. So this is a convergent and divergent nozzle has a throat area. So this is a throat, as you know, this is a throat area where the cross section area has minimum. Now in this area actually the throat area is given as 500 millimeter square. So in this area the area is given as 500 millimeter square and an exit area. So the exit area of the duct system is basically that. So this is the exit area. So this is the exit area. So exit area basically 1000 millimeter square. So this basically A2, that indicates A2 is equal to 1000 millimeter square. And throat area, so this is the throat area, it is basically 500 millimeter square. It is given in the numerical. Now air enters the nozzle. So this is the inlet, so this is the exit, and this is the throat. This is the convergent section and this is the divergent section. So air enters through this channel, through these sections, nozzle with a stagnation temperature. You know that the stagnation property or stagnation temperature is basically defined like PT and V like that. This is basically pressure, temperature, volume. When you define the stagnation temperature, volume, pressure like this, it is basically denoted with P0, T0, V0, corresponding subscript 000, right? Now the air enters the nozzle a stagnation temperature of 360 Kelvin. So 360 Kelvin. So that's why this area basically indicates this 1 this cross section area. This is star, that indicates basically throat section, and exit section basically indicate two sections. Now air enters, when air enters in the nozzle, the temperature is given as T01, means T0 means basically stagnation temperature, indicate at 1 means in section 1. So that is basically given as 360 Kelvin. And stagnation pressure is basically 1 megapascal. So stagnation pressure means P0 basically stagnation pressure. You know that P is basically normal pressure is designated with P, but stagnation pressure is P0. So that indicates P0 at which section? At 1 section. That's why it indicates as P01. That is basically 1 megapascal. And the value of A star means the throat area section, that is 500 millimeter square. Now you have to calculate the maximum flow rate of air that the nozzle can pass, and the static pressure, static temperature, and Mach number. So you have to calculate the maximum flow rate. So maximum flow rate basically given through this channel. Actually we already covered this topic. So you know that the maximum flow rate is occur in this section, in the throat section. So you have to calculate the maximum flow rate in this throat section, and you have to calculate the static pressure, static temperature, and obviously the Mach number. Mach number is basically as you know that Mach number is the ratio between V by C, the velocity of fluid divided by sonic velocity of or velocity of sound. So this is the ratio Mach number. You have to calculate the Mach number, static pressure, right, static temperature, and as well as the velocity. So you have to calculate all these things, but the condition is that when the nozzle, if the divergent section, so this is the divergent section. Now if the divergent section act as a nozzle, if this divergent section act as a nozzle. Second case, if the divergent section act as a diffuser. You know that what is nozzle and diffuser, already discussed on this. Now if these two cases, in same case, like in divergent section act as a nozzle and divergent section act as a diffuser, then you have to calculate all these terms. Okay, in this numerical, what is given that basically these are convergent, divergent duct and nozzle and divergent duct actually in this area. So in this section actually the exit area is given as A2, and the throat area, that is A star, that is given. The ratio between that exit area to the throat section area, that will be 1000 divided by 500 as it is given by your numerical. So exit area is given 1000 millimeter square and throat area is 500 millimeter square. So corresponding to this, the ratio will be 2. So A2 by A star will be 2. Now from isentropic flow chart, so this is the isentropic flow chart. From the isentropic flow chart, you can get, if you put these values A2 by A star is equal to 2, then if there are two possible values for Mach number, one for supersonic flow and another for subsonic flow. Now when it is supersonic flow, that divergent section act as a nozzle, and other the subsonic flow, because the value is for Mach number is basically less than 1. So basically the Mach number corresponding to A2 by A star from the isentropic flow chart for is equal to 2, that will be 2.197 for one case and 0.308. And where it is comes, just a minute. So now this is basically your gas table chart. This is your gas table diagram, and you know that A2 by A star, now this basically indicates M star, A by A star, P by P0, rho by rho 0, T by T0, in which you know that this is the Mach number, and Mach number maximum is Mach number at the throat section, that indicates A by A star. A is basically static area and A star basically the cross-sectional area when the fluid enters or fluid flow at the maximum flow rate. Okay, so this is the values. Now A by A star means A2 by A star. Now corresponding to A2 by A star, so this is here 2.03. So 2.03 here, and 2.03 also in these sections. So for for the two values of 2, you can get the Mach number is 2.20 and 0.30. From this table you can get the value is 2.03, corresponding Mach number value is 0.30, and corresponding to 2 value of A by A star, you can get the value 2.20 here. So corresponding the value of P by P0, you can get like which is basically used after the numerical. So 0.93947 for corresponding to here, 95638 and 0.9822832, and the corresponding these values, the value will be 0.09352, and the temperature T by T star will be 0.50813, which will be required for the numerical in the letter. Okay. Now, from the isentropic flow chart, as you know that the two Mach numbers you can get from the A2 by A0 value, A star value actually. So A2 by A star, as you know that value is 2. So corresponding two values, the Mach number you can get two values like Mach number 2.197 and one for 0.301. So when M2 is equal to 2.197, then basically nozzle act as basically when the fluid is flow through the nozzle, its basic flow basically supersonic type of flow. Because of Mach number here 2.197, that is basically greater than 1. Now from that chart also you can get the value of P2 by P0. Already we discussed that 0.0939 and T2 by T0. Now P2 and T2 basically the exit pressure, exit temperature, and P0, T0 basically stagnation pressure and stagnation temperature, which is basically denoted as at the inlet condition of the nozzle P0, T0, and T2 is basically here. Now and P2 and T2 here. Now as you know that P2 is equal to P2 by P0 equal to 0.0939. So P2 will be 0.0939 into P0, 0.0939 into P0. Now value of P0 is given as the stagnation pressure is 1 megapascal. You just convert into kilopascal here. So P2 will be this into 1000 millimeter, 1000. Okay, that will be 93.9 kilopascal. Okay, similarly, as you know that from the isentropic flow chart, when the Mach number value is 2.197, T2 by T0 from the flow chart, from the gas table actually, T2 by T0 will be 0.5089. So T2 will be 0.5089 into T0 value. T0 means stagnation temperature. Stagnation temperature in the numerical given as 360 Kelvin. So T2 will be 1832.2 Kelvin. Now, as you know, the sonic velocity means velocity of sound. The velocity of sound basically that is at the exit condition. If you want to calculate, so in this condition, if you calculate the sound velocity of sound, that will be C2, that equal to gamma under root of gamma r T2. So value of T2 is coming out from this equation, that is basically 183.2, and under root of gamma r basically 20.045, and under root of T2 that will be 183.2 here. Okay, so C2 will be 271.2 meter per second. Now you know that the Mach number, what is Mach number? Mach number basically, so Mach number basically the ratio between V by C, velocity of sound divided by velocity of, velocity of the fluid divided by velocity of sound. Now Mach number, so from this expression you can know that M2 is equal to V2 by C2. So from this equation V2 you can write C2 into M2, C2 into M2. Now C2 is coming out here 271.2, so this one, so that is basically your C2 into M2. So M2 here 2.197, so M2 is here. So V2 will be 595 meter per second. This is your exit velocity. This is your exit pressure, which you calculate exit pressure and exit velocity. You already calculate. Okay. Now the second part is that you have to calculate the mass flow rate, and you know that the mass flow rate basically designated. This is the mass flow rate that is basically from the continuity equation rho into A into V. When you calculate the maximum mass flow rate that you can get, maximum mass flow rate when you calculate, that will be A star into P, rho star into V star, that equal to rho 2 into A2 into V2 from the continuity equations. So from that equations you can calculate the mass flow rate. Okay. Now for air, as you know that for air from the when you calculate the critical properties with the relationship of stagnation pressure, so you can get P star by P0 for air 0.528, and as well as you know that the T star by T0 is equal to 0.833. Now from that equations, if you calculate the rho star, so rho star is equal to P star divided by R T star, is equal to P star. P star is equal to what? P star is equal to, as you know that P star is equal to 0.528 into P0. So 0.52 into P0. P0 means the stagnation pressure. Now stagnation pressure in this numerical is given as 1000. Okay. Divided by R. Value of R is 0.287 into T star. T star is equal to what? T star basically, T star is equal to 0.833 into T0. So 0.833 into 360, that 360 basically stagnation temperature. So from this expression you can get the value of rho star. Rho star will be 6.13 kilojoule per meter cube. Now when you calculate the rho star, you have to calculate the T star. Basically you have to calculate the star, basically subscript basically indicate the area of the at section particular at throat section. So at this corresponding area the temperature will place density, that now temperature will be 360 into 0.833, 360 into 0.833, that will be 300 Kelvin. Okay. Now as you know that the velocity of the at this section, basically at this maximum at this throat section, basically under root of gamma r T star. You know the value of T star means at this section the temperature, stagnation temperature means maximum temperature that you can get in the nozzle. So V star will be under root of gamma r T star. So gamma under root of gamma value will be 20.045, and under root of T star that will be under root of 300 Kelvin. What you can get now, V star will be 347.2 meter per second. That is your V star. Okay, and you know that maximum mass flow rate. So maximum mass flow rate, you know that formula, maximum mass flow rate is equal to A star into rho star into V star. Okay, so maximum mass flow rate is equal to A star. A star means the area of the throat section. Now area of the throat section given as 500 millimeter square. You just convert into meter. Okay, meter square. So that's why 500 into 10 to the power minus 6 into A star. So this is A star now. This is, and 6.13 is basically rho star. So this is the rho star. This is 6.13. Just put those here 6.13 into V star. V star means velocity at throat section. So velocity at the throat section basically V star. That is basically your 347.2 here. Okay, so 347. So maximum flow rate is 1.065. So all these parameters already calculate, like maximum mass flow rate, exit pressure, exit temperature, Mach number, and the exit velocity. Okay. So in the second part of the numerical, you have to calculate all this term like pressure, temperature, and velocity. Okay, and maximum mass flow rate. This is W. We have to calculate all this section. But when the Mach number is 0.308. Where it comes? It comes from the A2 by A star values, as we discussed. So A2 by A star basically what? That is basically 2. So corresponding to 2 isentropic chart, you can get the values, M values. That M values you can get 2 M values for 2.00 and M is equal to 0.308. For M is equal to 2, you already that when the M value is greater than 1, you know that the flow is basically supersonic flow. At the time when it is supersonic flow, you have to calculate all this term like pressure, temperature, velocity, all this time you have already calculated. Now in the second part of the numerical, when the Mach number is 0.308, that means basically subsonic flow, because the Mach number is basically less than 1 here, because 0.308, so that means subsonic flow. And so in this case, when divergent basically section act as a diffuser. So in the previous case, divergent section act as a nozzle. Now in this section, when the Mach number is 0.308, so that means divergent section act as a diffuser. Now, as you know that the P2 by P0 value is basically 0.39936, that comes from the isentropic flow chart or gas table chart. So P2 by P0, that means that P2 means at the velocity pressure at exit section, and P0 basically stagnation pressure. Similarly, T2 by T0 is 0.9812. So corresponding to this, you have to calculate from P2 here. So P2 will be 0.936 into P0. So 0.936 into P0. P0 is basically 1000. That is given in your numerical. So P2 will be 936 kilopascal. Okay. So from this expression, T2 by T0 is 0.9812. So T2 will be this one into T0. So this one into T0. So T0 basically 360. That is given in numerical. Now T2 is basically 353 Kelvin. Now as you know that the velocity of sound basically C2 for reversal adiabatic process, we know that under root of gamma R T2. And under root of gamma R T2, that means under root of gamma value is 20.045, because gamma value is for air basically 1.4, R value is for 0.287. If we put this value, we can get the value under root of gamma will be 20.45. Now the remaining under root of T2, now T2 value is 353 Kelvin. So under root of T2 here 353.2 Kelvin. Now C2 will be ultimately 116 meter per second. Okay. Now if you know the value of C2 and you know that Mach number is equal to V by C, and you know the value of C2 and you know the value of M, so you can get the value of V2 from that expression. If V2 is equal to M2 into C2, so M2 is your 0.308, that is here, and C2 is basically 376.8, that is here actually. So V2 is equal to 116. So sorry, V2 is equal to 116 meter per second, and you know that the mass flow is basically constant. So in the previous class, in the previous part of the numerical, already you have calculated the maximum mass flow rate, and the maximum mass flow rate will basically that is basically 1.065 kg per second. Okay. This is the new topic, so dimensional velocity, and basically the dimensional velocity, which is basically one type of one parameters that include in the compressible fluid flow, which is very important concern in your compressible fluid flow chapter. Now, as you know that the Mach number basically, as you know that Mach number is equal to V by C. Okay, V by C. That means velocity of fluid and yes, with respect to the velocity of sound. Now, when you change with m subscript, that means m star, that means when the Mach value is reached m is equal to 1, so Mach value is maximum, that means so m subscript is equal to v by c star, obviously, and c star will be written as v star. Why? Because as you know that c is equal to under root of gamma rt, or when it is changed into c star or c subscript, that will be changed into gamma rt subscript. So that is equal to v star. So in terms of that, you can write here that c star is equal to v star also. Okay. So in terms of m star or dimensional velocity, that also written as v by v star. Now, so m star, if you multiply, if you square with that, m star square is equal to v square divided by c star square. Okay. Or it can be written as v square divided by c square into c square divided by c star square, so that both will be cancelled up. So after equation will be same. So v square by c star square. So c square will be, if it is cancelled, then the equation becomes same with this one. Now, as you know that v by c is equal to your Mach number, so you can write this term as your Mach number. As you know that Mach number is equal to v by c here. So you know that in terms of v by c, that will be m square here. Okay. So the remaining portion is c square divided by c star square. So m star square you can written as m square into c square divided by c star square. Okay. Now, as you know that from adiabatic flow of ideal gas, as you know that from the adiabatic flow of ideal gas, like v square plus v square by 2 is equal to v square by 2 plus cp into t is equal to H0. From the stagnation temperature, stagnation properties, as you know that or stagnation enthalpy, that designated with H0, that is nothing but the summation of the kinetic energy plus Cp into T. Okay, so as you know that H0 also is equal to, you can written as Cp into T0, right? So v square by 2 is equal to v square by 2 plus Cp by Cp into T, that equals to written as Cp into T0, right? Now, as you know that v square by 2 is here same, plus as you know that Cp is equal to as you know that Cp is equal to gamma R. You know that, I think, from the basic engineering thermodynamics chapters. So you know that in terms of Cp you can written as gamma R divided by gamma minus 1. T is here, so this two will be same. So this equation becomes Cp into T, also written as gamma RT divided by gamma minus 1. Similarly, it can written as also Cp into T0, it can also written as gamma T0 divided by gamma minus 1. Now, why do you see that? As you know that C is equal to, under root of, for adiabatic flow, C is equal to under root of, under root of gamma T, right? So if it is happened, so in this equation, so that is basically gamma T. Now, if you written as C square is equal to gamma T, now it is here gamma T. Okay, this is a gamma T. In terms of gamma T, also written as here. So right here, so v square by 2 plus gamma T. Gamma T also written as C square. So that's why C square here divided by gamma minus 1 is equal to, similar fashion, C also written as C0 square is equal to gamma R T0 square, right? So this is basically gamma T0. So gamma T0 square, it also written as C0 square. Okay, sorry, not square. Gamma T0 is equal to C0 square, because you know that C0 is equal to T0, right? C0 is equal to gamma T0. So in terms of C0, it will be gamma T0. So in terms of gamma T0, you can written as C0 square. Now, you know that C0 by C stars is equal to, C0 is equal to under root of gamma T0 divided by C star is equal to gamma T star. Now, gamma will be cancelled. So that will be T0 divided by T star, right? Now, T0 by T star, you know that the properties like with stagnation properties, okay, stagnation properties from critical flow chapter, T0 by T star, you know that T0 by T star is equal to 1 plus gamma minus 1 by 2, sorry, into T0 by T star is equal to 1 plus gamma minus into 1, right? So these are equations. Now, if you put these values here, so if m is equal to 1, so if f is equal to 1, sorry, this will be minus. So if it is minus, okay, if it is minus, the equation becomes t0 by t is equal to t star. It can be written as under root of gamma plus 1 by 2. Right. Now, in terms of that, if b square by 2 plus c square by gamma minus 1 is equal to c0 square. So c0 is equal to c star into gamma plus 1 by 2 the whole square. So in terms of that, c0 or c0 square, you can written as gamma by 1 by 2 into c star into 1 by gamma minus 1. Now, if you divide c star square in this side, so that will be b square divided by c star square plus 2 divided by gamma minus 1 into c square divided by c star square is equal to gamma plus 1 divided by gamma minus 1. Now, as you know that v by c is equal to Mach number, so m star square in terms of v by c star square is equal to m star square plus 2 divided by gamma minus 1. So, in terms of c square by c star square, it also written as m square divided by m star square. So, that will be gamma plus 1 divided by gamma minus 1. Okay. Now, if you write this equation in terms of, so if you solve it, that will be coming out that m star square is equal to gamma plus 1 by 2 into m square divided by 1 plus gamma minus 1 divided by 2 into m square. Okay. Now, in this expression, if you put these values like m is equal to less than 1, if m is equal to less than 1, if m is equal to greater than 1, or if m is equal to 0, if m is equal to 1, or if m is equal to infinity. Okay, for both the cases, if you put these values here, m is equal to less than 1, if you put these values m is equal to greater than 1, the equation becomes m star also you get values like less than 1. Okay, if you put these values m greater than equal to 1, the m star will be m star that will be greater than also 1. If put these values m is equal to 1, the equation become m star will also 0, right? Now, if you put these values m is equal to 1, the equation m star will be also 1. If you put these values m is equal to infinity, that m star will be gamma plus 1 divided by gamma minus 1. So that is the conditions of different condition. If you put these values in terms of m, if you varies the conditions m is equal to 1, m is equal to less than 1 or greater than 1, you can get these values like this. Okay, sorry, that will be under square, so that will be under root of this one. Now, so this is the dimensional velocity of m star, and one question for you, that what is Mach number? Can you tell me that what is Mach number? So Mach number basically the ratio between the velocity of sound divided by velocity of actually fluid divided by velocity of sound. Now, what is the value? What is the condition for Mach number? If m greater than equals to 1, that flow is basically supersonic flow. Okay, if m less than is equal to 1, that is basically subsonic flow. If m is equal to 1, that will be sonic flow or sonic velocity. Okay. Okay, thank you very much for listening and watching me, and the next lecture video we will discuss on the normal shock and pressure distribution on nozzles. Okay, thank you, goodbye.